my screen here. Okay. All right, perfect. So thanks for having me. I appreciate the opportunity to be talking with you all here today and hope that for many future discussions and collaborations between our institutions, and really excited about talking to other folks who are interested in practical applications of ontologies and really that sort of data-driven ontology applications. So the talk today is called Enforcing Ontological Commitments from Process Mining to Dependent Types. And this really covers work that we've been doing more recently on the process mining side and the more type theoretic dependent type side of things. Is work from a couple of years back, but I thought it's based on discussions that I've had with John in the past before. I thought it's relevant to the group and um, can kind of find a through line between the two to intersect them. All right. So at the heart of this whole kind of problem is what I'm calling the semantic gap. So this basic idea of we have the real world, right, full of all kinds of complex phenomena, a lot of different things going on that are difficult to understand or can be difficult to represent, and that's being translated into some kind of data. And obviously, in this very simplified diagram here, we have the arrow doing a lot of heavy lifting. And we know that in reality, it's not so easy to just simply translate or capture what goes on in the real world with um, some data sets. So perhaps a slightly better way or more accurate way of looking at it is like a distillation, right? Where we have the real world is this sort of messy substance that we want to more accurately represent. So we've got some kind of like information systems or some method of representing it, and we're just getting these kind of like little drips, these little representations that maybe start to describe the real world and is useful for some purposes. But of course, we have a lot of this kind of leakage here of knowledge of the real world being lost. And as data scientists, analysts, ontologists, we're faced with a lot of um, issues of reconciling this and dealing with this process. So when we think about the role of analysts in analyzing this data, when you're coming up against this whole kind of problem, and interfacing with it, there's a lot of different ways that you can attack this problem because there is just a the gap between what's represented in the data. Maybe the data is missing some components. It doesn't quite accurately represent things. It might not be at the right level of granularity, and you'll have specific kind of needs for your analysis. And inherent in that interpretation and analysis of the data necessarily are some kind of ontological commitments. So you're making certain views of the world based on the way that you're filling in missing values, perhaps, removing duplicates in your data, all sorts of different interpretations that you're enforcing. And a lot of the time, I would say, for typical kind of data analysis, that's done in an ad hoc kind of way. And it's going to be implicit or informal kind of ontological commitments in this way. So to bridge this semantic gap, we need to firstly recognize that data analysis necessarily relies on these external ontological commitments to make sense of that underspecified and incomplete data. And so our goal then is to integrate those commitments into data-driven systems so that we can enable reusability, transparency, verifiability. And in the context of this talk, I'm going to be grounding that in a couple different examples here. Firstly, of process mining. So what are the ontological challenges of events as they're understood in process mining data? And how do we formalize the different way that that data is interpreted in that context? And next, more broadly, for data types and how they're used in data science, what are the limitations of simple data types that we're very used to, like strings, integers, etc.? And how do we make the types themselves actually more meaningful and able to capture more of the real world? So we'll begin with the first part entitled Mining for Meaning, which is focusing on this process mining side of things. So to sort of set the stage and provide a little bit of context, business processes, right? These are a kind of lens that many enterprises, organizations use to understand how they create value and sort of contextualize um, their operations. And so many times the models that are associated with this will look sort of like a flow chart or are understood, as some sort of procedure with given inputs and outputs. And in the context of process mining, we have the process data, which is in the form of an event log. So this is basically a record of what happens. So you have events and timestamps, and you're sort of just recording different sets of observations. And we're combining some implicit knowledge here, right, about the process, various kind of business rules to arrive at some outputs. So process models, compliance checks, we want to verify that certain things are happening, maybe because there are regulatory requirements, and different insights about the process. Like might want to look at what our lead time is. So process mining is really that engine of analysis for event data, and it incorporates a wide swath of different analysis techniques on that kind of data. So to get a little bit more concrete and motivate this a little bit more, let's take a look at example. So this is an example of a simple event log where we've just got a few columns. So we have our timestamp, so things are happening over time, right? We have these set of observations. And this is for like a healthcare example. We can see that even without a whole lot of domain knowledge ourselves, we can recognize that some issue is inherent here, that we have this patient intake event twice for the same patient. And it probably doesn't make sense to have to do the intake twice, right? Like this is only something that should occur once. But this knowledge that this issue exists is something that's entirely external to the data. So we can identify that issue, and maybe our chosen solution is that the event label was in fact wrong. So we have some information system that did not accurately depict what was going on in the real world. And we want to make some kind of correction to say, actually, that was an additional screening step. And importantly, this is entirely external knowledge that we're applying in order to interpret or make corrections in that data. Another issue that's prevalent in process mining is the problem with events themselves. So the central element being event logs, you have different labels for what the events are, and they're treated as one homogeneous kind of entity. So events are events, right? They all describe one sort of instantaneous observation. But when you actually look, even just in terms of the natural language labels given to events, they denote a lot of different process concepts. So these are all real world examples taken from real enterprise process data sets, event logs. We can see like awaiting assignment, document under review. So these elicit a little bit more of that like status, like a state of sort of concept, whereas review document, for example, might be more of like a process step. So something that has begun to occur or maybe has just finished occurring. So these are all flattened to the same sort of event view, but their implications for the process at hand are very different, right? So events are something that are very heavily overloaded and require interpretation for us to analyze them in the process mining context. So going back to our view of process mining, we have a couple questions to guide how we're going to think about ontologies here. So firstly, where does a process ontology fit in here? How do we integrate it with this high-level workflow? And what are the tools for us that enable that fit? So the challenge for process ontologies more broadly, if we want to try to answer this question, is a lot of the ontology applications, especially for very expressive ontologies, are more focused on representational, access-driven, as in OBDA, or use as a referential or sort of conceptual model. So we instead want to focus on how we formalize the ontological commitments that are inherent in data analysis, and we use the term operational realization to capture this notion. So sort of disambiguating the broad term of ontology application to really mean this data-driven understanding. And how should we apply this to process mining? So here we have just a high-level overview of sort of the traditional view of process mining and various elements of it, and what is the more formal understanding of them. So where we go from the raw event data, instead we want to form a knowledge base where there are ad hoc interpretations embedded in our analysis. We instead are creating something called a data theory, which I'll explain in a little bit more detail in a few slides, where we have business questions. Those are logical queries, and any sort of validations should correspond to logical proofs. And this can be understood in terms of three sort of broad steps of map, formalize, and analyze. So beginning with the mapping portion of this, if we want to take event log data, so here we have another example where we've just got a few columns, timestamp the event, and then we have something called a transition. And this sort of marks either beginning or ending, or it can also describe things like scheduling, starting, skipping. But in this case, we're just interested in the start and end markers of some occurrence over time. So as we're looking at this data here, even before we begin the mapping process, we can see something that's a little bit unintuitive, entirely independent of whatever domain we're talking about here. So we see that at 1530, we have a credit check complete, and at 1538, later in time, we have the start for that same activity. So intuitively, this should not line up with our basic foundational knowledge of processes, because we know that something cannot finish before it started, right? So seeing that complete before the start doesn't really make sense. So if we want to map this and try to discover that problem, first we'll take a given row here. So if we take a look at the first row, we'll have a set of literals that we can generate, and we can do the same with the second row to reach our ground data. So now that we have that ground data there, we can use what's called an ontology translation. So going from this very simplified set of relations that are very ontologically neutral and mapping that to some foundational process ontology. And in our case, that is the process specification language ontology. And we can see how we map into that language. So here we have an axiom from our ontology that says if any two events share an activity, right? So these are both talking about a credit check, and there's a start and an end. Then there is this thing called an activity occurrence. So something happening over time. And we can view that sort of on a timeline, right? We've now inferred the existence of a new element of our domain to go in our knowledge base called an occurrence. And we see that it has a begin of and an end of. And intuitively, we know there's a problem here, right? Especially with this timeline visualization, we can see that this doesn't align. But let's see how we actually discover that. So now that we have our data translated into the language of our ontology, we want to apply our formal knowledge of the processes in general. And we can look at the axiom from our ontology that says activity occurrence start points are less than or equal to their endpoints. So things don't end before they begin. And we can combine those together in our reasoner, and we can reach a proof of inconsistency, right? This is not consistent with our foundational process knowledge. And so that's all well and good for the domain independent side. But what about when we want to incorporate elements from our domain? How might we extend our process ontology to model that domain process knowledge? And we want to focus on how we standardize and make it more tractable in terms of having a standard and scalable way of applying the ontology that doesn't necessarily require deep insight and understanding of the ontology, so that it can be used by process mining practitioners and data analysts rather than only ontologists. So the elements that we're using here are what's called knowledge patterns, which abstracts elements of the ontology and into something called a data theory, which I'll go ahead and explain here. So to get the intuition for knowledge patterns, here's a couple examples of some domain-specific process knowledge that is instantiating parts of our process ontology. So something that looks fairly specific, right? To say that maybe I'm dealing with some kind of manufacturing scenario, and I want to say that when a fragile object is dropped, it breaks, or our earlier example from the healthcare domain saying patient intake only occurs once for the same patient. Now, these are domain-specific things, but if we go ahead and look at um, elements of these that come from our domain, right, we can look at all the parts around it, like the white parts here, and generalize and say, this is really not all that specific, right? And this kind of behavior that we're modeling in general would be something that we want to model to all kinds of different processes. So the first example would be a state-based effect, right? So it's very common to processes that we want to model to say that something is true beforehand, something happens, something else is true after that's happened, right? And similarly for the occurrence constraint. So we have some sort of activity and we're saying it should occur only once, right? Like some things may occur a certain number of times, exactly once, between 2 and 3 times. That's something that is going to be very common to many different um, domain processes. So let's take a look at what that looks like and how we specify it by zooming in on the state-based effect example. So a state-based effect, we have our specific example here, and then the like natural language explanation of it. So we have some initial condition holding, something happens, some occurrence happens, and then there's some resulting condition that holds afterwards. And we can recognize that the pattern is abstracting some kind of common process knowledge such that we can instantiate it and call it sort of like a function um, to declare that domain-specific knowledge. So in this case, we would simply call state-based effect with the arguments being fragile, the initial condition, dropped as the occurrence, and breaks as the resulting condition. So what that looks like, more formalized in terms of the language of the ontology, is we can say a state-based effect is an axiom of this form, where it has the following free variables, right? So this is our pattern definition, and then we can instantiate it. So we can say the concrete extension of our process ontology that implements this pattern looks like this, right? So we've taken these placeholder free variables and we've used elements of our domain vocabulary to actually instantiate something specific. Okay. So if we ask ourselves, in the traditional understanding of a knowledge graph or an ontology application, where this fits in our current sort of ecosystem, right? Is this thing part of our T box? Is it part of our A box? Or perhaps, we consider this part of a domain ontology. And for our purposes and the way that this is applied, we call this part of the data theory. So because it is particular to a given um, data set in our domain, and it might be driven by particular analysis needs, different analysts will have different kind of um, goals and level of granularity that they're viewing the process at. So we want to separate it from the domain entirely and instead view this as the data theory. So going from our traditional notion of A box and T box, instead for the data-driven process ontology view, we have the raw data and our mappings in order to produce our initial knowledge base, so our set of ground facts. And on the other side, we have our process ontology, which is at the foundational domain independent level. And then for our particular data set in our domain, we have our data theory. Okay. So on to the second part, dealing with what is in a data type. So data, as we acknowledged earlier, is representative of real-world phenomena, and we have this kind of semantic gap between what we can possibly represent in data and the complexities of the real world, right? And often that data is going to be encoded using simple data types, so integers, strings, floats, maybe date time if you get a little bit more complex, right? But that being said, these are all just simple data types. So the core argument here is being that data types do not really typify the real world, and real world constraints are very, very difficult to handle and pack into data types. So to give an example of this, right, take a look at this sign here, and immediately we can see that there is an issue occurring here, right? We have this total, which is sort of nonsensical. But from the perspective of the types that we're using, I mean, these are all integers, and the plus operation over integers is completely valid. So this must be a valid operation, right? However, we know intuitively that that's obviously not the case. So where in the real world we have all kinds of implicit rules and complex concepts and relationships, simple data types have this very flattened view of saying numbers are numbers, things are strings or they're integers or floats, and we have to sort of pick a lane and kind of stick there and just hope it works out. But we have, of course, this semantic heterogeneity inherent in here, in that the same data type is representing many different kind of concepts. And to illustrate that this isn't just some sort of like toy example, right? Of course, it's a little bit of a silly joke and a little bit of humor, but there's really actual concepts underlying this. So we have things like a geospatial region. You could also make the argument that you're talking about a given geopolitical entity, right? Because the uh, borders and boundaries can change over time. So maybe it's not always a geospatial region. We have population metrics, which are going to be core to looking at like census data, for example. And we have things like distance. So let's take a look at how this actually manifests itself with a specific example. So here we have a table from COVID-19 vaccination data. And let's take a look at what's going on here. We have dates being recorded. We have the number of people fully vaccinated. And then we have the percentage of the eligible population that's fully vaccinated. And to illustrate the problem of part-whole relationships or the mereology that is underlying this and the complications it can cause, we'll take a look at what's going on here. So here we can see that the number of fully vaccinated has gone up, but unintuitively, right, the percentage of the eligible population goes down. And this may be due to the actual set of fully vaccinated, that definition, including a new part in that previously the vaccine, wasn't properly tested and wasn't deemed safe to be administered to children, and now it has been. So that's changed our interpretation of this data, despite its data type and the column name all remaining the same. And similarly, if we look at this next one, we can see the number of fully vaccinated. We may expect a monotonic result here to say that it's always increasing, right? We can't unvaccinate people. However, we see that the number of fully vaccinated has gone down over time. And this could be due to the result of the definition of fully vaccinated going from 2 doses to now 3 or more doses. Yet our simple data type of account represented by an integer can't possibly handle this kind of knowledge. In terms of geospatial mereology, so here in Toronto, back in the late 90s, there was a thing called amalgamation. So you have these 6 boroughs of Toronto here, and pre-1998, when we talked about the city of Toronto, it meant this yellow region here. But post-amalgamation, the city of Toronto now encompasses all of these areas. So if I want to do some kind of analysis and get at the heart of what is the population of Toronto, how has it changed over time, this is something that I will need to understand. And if I want to be careful about potentially double counting and make sure I'm making apples to apples comparisons, I can't just rely on a simple integer encoding to be able to capture something like this complex geospatial mereology over time. So there's also the issue of provenance. So not only is it difficult to initially represent the data, but as we actually do the analysis and combine values together, the meaning of the data itself changes over time. And to make that more concrete, let's take the example of a special kind of distance metric. So say we've got a couple of people, Bob and Alice, and we take a meter stick or we take a measuring tape and we want to measure their height, right? So we can get Bob's height and Alice's height. And our intuitions may say, if we want to do any sort of operations with these, if we just figure out the units, right, we make sure they're both centimeters, inches, feet, whatever, then everything should be good, right? So if we have a proper ontology for units of measure, say, and it can do automatic conversions, then that gets us a good deal of the way, right? Our problems with data types are all solved. However, if we consider this kind of operation where we want to combine Bob's height and Alice's height, we're now dealing with a different kind of quantity. So the interpretation for what this result is no longer the height of a person, even if it can be measured in terms of the same units. We ensure the units match up. This sort of notion of the height of a total person doesn't really make sense here. And any downstream operations we want to do with this intermediate result needs to take that into account to ensure that our results are interpretable and we're not making any sort of mistakes. So if we take a little bit of a step back and ask ourselves the question relating to totals. So when we're talking about data operations, and in this case, talking about a sum, what can we meaningfully measure the totals of? So where does that make sense? Where might it not make sense? And let's look at a few examples and think on that for a second. So we have the example of the population of a total region, the height of a total person, and the temperature of a total region. So if we want to have this kind of property, or this result that holds to say that the property of their mereological sum is equivalent to the arithmetic sum of properties. So in simpler terms, saying that the property of A and B combined together is equal to the property of A plus the property of B. So for our first result here, right, that holds up, seems to hold up fine. If we take the total population of two neighboring cities, it's the same as adding together each of their populations. That's the population of the total region. However, well, that might be a valid operation in terms of how we're aggregating things for a person. It doesn't have the same sort of domain, right? To say that the height is a thing that operates on a singular individual person. And if we try to extend that property to this concept of a total person, that's not really a meaningful concept. And then slightly different, but also not a valid interpretation, would be talking about the temperature of a total region. So we may want to measure the temperature at a smaller place or a larger place, but we know it would be inaccurate if I said the total temperature of Toronto and Buffalo is equal to adding their temperatures together. Of course, that makes no sense at all, and we need to be more careful about what method of aggregation is allowed. And also, there may be some other considerations like the fact that the region that I just described would be a non-convex region. And so what really is the total temperature of that region, or what is that total region? So for provenance, we want to ask ourselves how we can formally represent those real world rules about quantitative data and how do we integrate provenance in them. So not only making the types more meaningful in terms of how they're initially represented, but ensuring that as we do our analysis and we perform different operations on these quantities, that carries through and we see the interpretation changing over time. So our basic idea here is to make the types themselves stronger and make type safety, meaning our program compiles basically that our types all sort of match up and make type safety a more meaningful result, as opposed to a trivial result of saying, the addition operator expects two numbers. As long as I have two numbers, that's type safe, right? It type checks. So that's a valid result. So how can we enhance that idea? So the basic idea behind our meaningful type safety framework here is to leverage the power of dependent types. And to give you an intuition for what a dependent type is, as opposed to simple data types like we have been talking about before, this is where the types of variables themselves depend on values. So where we might have the simple data type of integer, right? We can instead describe a dependent type called natural numbers. And those are integers where their value is greater than 0, right? So with those, we can enforce preconditions for operations. And I'll take a little bit of a moment to acknowledge the syntax here because there may be varying levels of familiarity with sort of this notation for describing types, and this is more sort of like a functional programming, like Haskell-like notation. So I say I have this operation called region sum, and the colon just denotes that this is the type of relation, right? The type of region sum is this type. So what is this type? I have this thing called disjoint that is true over my list of regions, and I return a region, right? So this is getting at the fact that I don't want to double count. So from the earlier example of like Toronto pre and post amalgamation, if I wanted to take one of the regions that went into Toronto and then sum that up into what we understand today as the city of Toronto, that would not type check here because it would be violating this disjoint condition. And note that this is entirely within the type checking. So this is not at all a runtime check that we're performing, and this is entirely dependent of what the function actually does. So in this way, we're separating the actual data operations that's occurring in our program from these preconditions. So our program can do whatever we like in terms of what it does at runtime and what that operation actually means in terms of adding them together. Maybe this is represented by coordinates or some other region, but that is independent of our types here. As well as to the issue of provenance, right? We want the types to meaningfully reflect what we do to them. So they change after we apply different operations. If we take the population average function and apply it to some list called regions, then the type of that result is an average over regions. It's no longer a region, it's a new thing. So this could come up, for example, if we're filling in data, say we have some missing values in census data, and we want to impute it by taking some kind of average. This gives us the tractability that this average over regions will propagate throughout all downstream operations so that we can see that that was not a measured quantity, but instead a derived quantity, which may impact our analysis and give us better insight into how we interpret those results downstream. So to give an example of what this actually looks like with some instance level data, we can encode those real world constraints through type checking. So if I want to do a population average, let's take a look at what I'm calling here. So say I want to take the average between two different difference operations. So first I have Toronto 2024 minus Toronto 2016, right? So this is the population change over time. And then the next one that I'm averaging is a difference between Buffalo measured in 2024 and Albany measured in 2024. So intuitively, we understand that, well, this would be valid to compute and actually obtain the result for. It doesn't give us a meaningful result in terms of our intuitions behind population average. If we're taking the average over something, it should be over the same sorts of things, right? These should differ over the same variable. So if I want to see sort of average change or average difference, those are distinct concepts, and I don't want to be mixing those. So we can reconcile this operation that we're attempting to do with the actual type of the population average function, which we can see takes a list of populations. And then we have the precondition that it differs over time with an exclusive or differs over region. So we either have one or the other, and we don't have both, and we return the resulting population average. Okay. So what about how this relates to formal ontologies and what guarantees can be made as it corresponds to logical consistency and type safety? So from the important result in type theory called the Curry-Howard correspondence, we know that types are the same as proposition and proofs are programs. And well, theoretically and at the fundamental level, that is something that we can leverage. We should be able to show that correspondence to say that ontologies can be constructed, which represent that type safety, and vice versa, but with the asterisk here that actually doing that in practice producing those proofs is a tricky thing. And we have results where we've done preliminary steps in proving that correspondence, but to really flesh that out and get those full soundness and completeness proofs is an ongoing area of work, and more study needs to be done to really make that logical guarantee sound. Okay, so taking a step back and looking at the takeaways across both of these different topics, um, reaffirming that motivation that we need to build ontological commitments that underlie analysis directly into data pipelines because it enables verifiability, reusability, and transparency. So taking this new angle to ontology application and really enforcing um, recognizing that ontological commitments are a necessary part of data analysis, and we should be careful to um, incorporate those explicitly and formally. Next, the idea of process data theories are a pragmatic and modular way for us to model event data interpretation with a particularly useful application in process mining. And it allows us to separate the data-dependent definitions from our foundational logic as represented in a process ontology. And lastly, for meaningful type safety, this gives us a powerful a priori approach so that we can enforce foundational rules as type checks to prevent invalid operations. So taking a look ahead, the one thing that I really want to call out on this section specifically is work that we're currently doing, and we're looking for other people to join in and posting this challenge out there to say we're developing process ontology benchmarking methodologies and ones that are data driven and motivated by real world data and scenarios. In our case, taken from process mining. So we want to provide new data-driven challenges for existing foundational ontologies that represent processes so that they're able to demonstrate their capabilities for this operational realization notion. So the application of the ontology to actual answering real-world problems on real-world data at scale. We're also working on extensions for object-centric event logs. So this is, we were looking at the more simple event logs before, but there's a little bit of a push to get the data a little bit richer and represent more complex relationships. So the framework that we've built out that I alluded to earlier, which is currently in the form of a Python library that implements those knowledge patterns, and that's in more detail at the QR code there if you want to take a look at that, and incorporating event knowledge graphs. And lastly, as the interface to this kind of library that I was alluding to, we're looking at applications of large language models so that, for example, rather than a user requiring comprehensive knowledge of all the library of knowledge patterns that exist for a given ontology, they can express in natural language their understanding of their domain and their process constraints, and the LLM can match that up and retrieve and instantiate the relevant knowledge patterns to create the data theory. And with that, I'd like to say thank you so much for having me today, and I welcome any questions and discussion points that you may have.
Thank you very much, Riley. That was fantastic. So the floor is yours. Participants, we have any questions for Riley? Yeah, go right ahead, Aaron.
I got a question. So I was really interested in the SBEs that you were talking about earlier. And I don't know if you one, I didn't see a graph like an axiom of it, like you had the formula, but like I'm curious what that would look like as an axiom. But really, it's people want business rules, right? Like, and that wasn't a business rule. A glass falling, it breaks, right? But people want business rules, and I've seen some techniques to get them into ontologies where they're directive ICEs or something like that, and then they do some comparison to them. And I'm not satisfied with any of the approaches I've seen. I like this approach were you thinking of business rules, and what do you think about treating business rules as SBE? Obviously, they will become nonsensical. Most enterprises contradict each other, eventually. So it's like, well, that is the rule. The rule is we don't send packages out, Monday through Thursday, and you only send packages out on Thursday to Friday. Well, what happened? That's something doesn't add up there, but that's the rule. But I'm going to be quiet and see what you think of those
Right.
questions.
Yeah, no, that's absolutely something we're considering and have in mind for things like this. So this is like a simple demonstrative scenario, but you can imagine in the past we worked with one of the big Canadian banks, BMO, at and their compliance issue remediation process. So when things go wrong, how do you return that to a state that you do comply with certain regulations or auditing requirements or things like that? And that would be part of what goes into that um, data theory to say, like as a state-based effect example, if a certain status is true of the customer's account prior to you trying to issue a line of credit, for example, then you would want to either like approve or deny that. So you would have like a maybe like acceptable or unacceptable state holding on the client's account, as an example.
And how did that work out? Like, did you actually do that, and was it efficient, and it wasn't
Yeah, so in
it
that
wasn't fragile? I guess
particular,
fragility is what I'm concerned about.
hmm, yeah, so in terms of extending this at scale and working with an industry partner, that's still something we're working on. Like in that particular project, we got to the stage of more the conceptual side and building out the ontology and using it as um, a model of reference, but we're still working with some organizations and actually applying this. But we have applied it in terms of some of the benchmark data sets that are out there. So in process mining, there's a thing called the Business Process Intelligence Challenges. And there's a bunch of different data sets. There's some from like Dutch municipalities. There is a Dutch financial institution. A lot of them come from the Netherlands, or there's Volvo IT Belgium has a log of like service incidents. So we've applied the knowledge patterns and data theory to those particular data sets.
Okay. Yeah. And then do you have this more as an axiom, or is that is it's just in this logical notation?
Yeah, so this is for us, like in our work in our lab, most of the ontologies that we write are in first order logic, and then that's encoded in like um,
Oh,
common
that's good.
logic format. Um, so for some of them, if you're asking in terms of like OWL axioms,
Yeah.
because sometimes it is going to be more expressive, it may or may not be possible to encode them. So
Got
like
it.
the earlier example of this ontology translation, for example, this would not be something that you can express in OWL, where you're inferring the existence of a new entity that is not a subclass or parent class of any of the entities here.
Correct. Yes. Yeah. That's very frustrating that can't do that now. Yeah. Okay. Thank you.
No worries.
Any other questions?
Yeah, Werner here. I have one. So the first part of your presentation and explicitly what you are explaining now, what is currently on the screen, is something that I've been working on since 2005, and I called it referent tracking. It's trying to represent everything by means of really uniquely identified things about which then
Mhm.
make the statements of this form. The remaining part of your talk reminds me quite a bit of the semantic databases from the 80s. Are you familiar with those?
Right. I've recall doing it, and you'll have to forgive me for the dependent type theory work being a little bit further back, so I have to sort of rack my brain. But I do remember, particularly when were submitting the paper, we had to add a few references to some of the the database work, but I think the real um, the critical standout behind it was in the provenance aspect. So while you could do um, like integrity constraints and things to match these sort of like preconditions, if you wanted to have this sort of um, thing being true, so that after a given transaction you do an operation, the type actually changes. I think that's where you see the novelty, and also in the formality in terms of the um, types as proposition and proofs as programs is something that doesn't have the same analog in the semantic database work.
Yeah, that's right. Because they rather try to prevent mistakes to be entered in the database, right? And
Right.
you are trying to figure out if a mistake has been made. What sort of a mistake can it be? And would it be possible to correct it automatically or give it the correct interpretation? Which I think in many cases, of course, is not possible. But at least if you can, then you can flag those cases where you can't find a definite unique solution, right?
Right. Yeah,
Yeah,
I think
that's
it's
yeah,
preventing them like before they occur. So not even letting the user run the program. It won't even get to runtime to try to do an operation like this. It's going to not type check and say that this is not type safe, and I can guarantee that this is not a valid operation.
yeah. Okay, thank you.
Thank you.
All right, up next, anybody else? I have some comments, obviously. When we discussed, or when we previously met, I was taken by the what I'm an advocate for, which is like shifting some of the ontology engineering as a static product that's being developed in our communities and more of it something that's executable. And in particular, I think in terms of execution iteratively over time, I mean, as execution often is. And so I think of it in line with automated verification, validation, and tooling of that sort, but I think gets right into the space you're talking about. And so like I'm a fan of like TLA plus, temporal logic of actions, modeling
Mm,
spaces, and then you kind of iterate them out or let a machine or an inference engine iterate how the states will unravel. And then you get to ask questions against those unraveling states, like, will it ever do this? Will it not
right.
that? And this is a great way to evaluate, say, if you're, Amazon, you're trying to figure out who to or where to invest what on your hardware team. It's great if you can identify where the most likely problems are going to occur downstream, if you can model the states. And so I'd often thought of and have done a bit of like taking ontology work and just kind of translating the axiomatizations of them into state transition diagrams and then execute
Mm,
for those so I can evaluate as new data is added to a data set against these certain constraints, what's going to happen and what's not. And then in fact, but I'll tell you, so other than what I've seen here, the closest I've seen anybody do anything like this, this actually links up to what Aaron was, I think, pointing to with the business logic, is this company Emandra. And I believe they're doing what you were describing in the finance space. So they work with finance companies and they basically model like at least the best case scenario they have is they model algorithms for like swaps and trades in the market
mm,
before they're actually approved. So when like a company goes public, they have to like write an algorithm or describe an algorithm that says we're going to allow these sorts of trades, and they can't do it in such a way that it will allow some kind of unfair leverage, and so that has to be evaluated, and it's often done manually. There's very rigorous kind of algorithmic swapping that's being described, and so this company comes in and they model that using reasoners like first order logic and reasoning engines,
oh,
identify the business rules around what can be done and what can't be done to identify potential leverage gaps. Of course, it works in a space like this where the world is rigorous. The world is not always so clean and
right.
clean. But nevertheless, that's a word of caution, not a word of like despair, right? Like I think you're pointing to some cases where the world does seem to be a little rigorous, and we as ontologists often think in these terms as well. So I wanted to just throw that out there. Less a question, although question coming. Curious are you guys engaged? Are you thinking about lining up with a formal verification research and literature? Is that something you're familiar with? I feel like there's a whole suite of tools out there that can be leveraged, like Alloy, TLA Plus, Imandra, even they have open source tooling that might, you might find some friendly faces over here.
Right. Yeah, it was a path that we were um, sort of exploring, I think within the context of my work directly and where it's been going in terms of the process mining application. Um, we're already kind of between the two worlds, like it's in that it's interdisciplinary work, and that we have the certain set of requirements from the process mining folks who really want to see data-driven, like applied stuff, and don't entertain the philosophical debates too much unless it's directly relevant. And then the applied ontology, which is a little bit pulling in another direction. So we hadn't really gone down that road a lot. In my master's thesis, though, where this work is from, we do have this like correspondence theorem to show um, like a correspondence between type safe programs and logically consistent theories, but there's definitely more work that can be done in that space.
Yeah. If I were a betting man, I think work in that space will be incredibly impactful in the next
Mhm.
5 years. But I am a betting man for what it's worth. So uh any other questions, comments, concerns, or compliments? We always like that.
I would like to jump on the compliment train if it's going, because this is really great work,
Thank you.
Riley.
Thank you very
So
much.
I'm working with Aaron over here. Uh, I want to say many of your core examples of homogeneity of data types and the ontological commitments that go into them. Man, I have seen them in the real world. Some of them, I gotta say, I was taking screenshots and sending them to coworkers because they were just dealing with it last week.
Oh,
So this
that's great to
this
hear.
is entirely relevant, and I really appreciate not only going through this but also being rigorous to be clear on what's the heart of the problem, and you articulated it really well. So kudos to you, sir.
Thank you very much. I'm glad to hear that. Thank you. I think it's very important in terms of not only using ontologies as um, a means of obtaining consensus or using it as a conceptual model, not to downplay their impact that they can have in those ways, um, but to ask a question deeper than can my ontology represent this scenario and how would it represent the scenario, but can it integrate with data? And recognizing that, especially for um, more complex ontologies, that's not always a really simple answer to get to that result, to map between some data sets and to, rather than let it be the Wild West and let everybody kind of interpret the ontology the way they want to and figure things out as they go, but to um, have a formal means of doing that. And that's kind of what the data theory that we're talking about really provides, to be able to abstract parts of your ontology and say, hey, here's a library of patterns that you can use. And it's exciting in terms of um, maybe the use of LLMs to put that at the forefront. I know it can be a little bit touchy when I talk to certain parts of the applied ontology space about the use of LLMs, but I think um, if you're using this sort of black box sort of thing at the beginning stage rather than in place of the reason or in place of the proofs, I think that's where I can see the usefulness and the power of it being a lot more convincing.
Certainly am on board with using them as something like glue.
Yeah.
They can stick things I know work together. Well, fantastic, Riley. I have to second John's comments. This was excellent. I'm so glad you joined us. Loath to jump into another question with 1 minute till, but thank everybody for attending. You scan that QR code if you want more information. Riley's not a hard person to find if you Google him. And again, let's thank our speaker. Hopefully
Thank you very much.
Thank
Thank
you,
you.
really.
Great
That
job.
was fantastic.
Thank you.
All right, take
Have a
care.
great Halloween, everybody, and go Blue Jays.
Definitely.
Blue Jay.
Take care, man.